the first type of heat capacity we're going to consider is the constant heat volume heat capacity, or otherwise known as the isochoric heat capacity. To at least explain what this heat capacity is, what I want you to do is let's first consider a system, a sort of piston cylinder system in which the piston is locked into place. So let's consider a piston system where the piston is locked into place. And so we have a piston cylinder system that looks like this, where our piston is here. Our system, which could be a gas or even a liquid. There's just some sort of fluid underneath the piston. And the position of the piston is stuck into place with a lock. Okay? Because that piston is locked into place, the system has a constant volume. Now, to this system, let's say that we add some heat to it. And as we add heat to the system, because the volume is locked into place, that means the temperature and pressure of the system are going to change. Alright, so that's the premise. So for this system, let's consider, or let's develop, the closed system energy balance. And so, let's write out our closed system energy balance equation. Delta U plus delta EK plus delta EP is equal to Q plus W. Let's now simplify this energy balance and get rid of terms that don't really matter. Delta U matters because the temperature of the system is changing. The kinetic energy of the system isn't changing because nothing's accelerating, so we could say that's 0. The potential energy of the system is not changing. This is also 0. We're adding heat to the system, so clearly this is an important term. But the system volume is not changing, right? So as far as work, if our system boundaries aren't moving, we don't have any shaft work, and we don't have any other type of work, so we could say that the work term is equal to 0. So what we're left with is Q is equal to delta U. What we'll now do is let's now divide both sides by some sort of mass, the mass of the system. And so that way we get a specific heat is equal to a specific internal energy. So now let's go back to our heat capacity definition from the previous video. So our heat capacity, C, and I'll put the subscript V here to show that it's constant volume. From its definition, we said it's equal to the specific heat divided by delta T, as delta T goes to 0. From our energy balance, we know that our specific heat's equal to the specific change in internal energy. And since we're taking the limit here, this is the definition of a derivative, right? And so, what this means is that our constant volume heat capacity is the partial derivative of the internal energy with respect to temperature at a constant volume. Right? And so just to be a little bit more explicit, CV is directly equal to this. At constant V. I guess I should say this is a specific volume since we divide it by mass. Alright? And so, your heat capacity, the way you would measure it is if you had a plot of your specific internal energy versus temperature. The slope of that plot would be equal to C